And all right, so now we want to know, can this algorithm get stuck in a local maximum? And it can't. All right, so we're going to have to prove that it can't, and it's a little tricky, the proof, because you have to remember what we want to prove is that for every graph, for every network with edges and capacities, for every choices of how we augment this path, we're guaranteed to find, not get stuck, and we're guaranteed to find a global optimal, right? And this is, in some ways, quite a surprising thing, because for most problems of this nature, they're what we call NP complete, and we don't have algorithms for it, right? So this gives us a fast algorithm for solving this problem. And if my father was here, he would really push this idea of witnesses. The reason there's an algorithm for this is because as you get a better and better path, you have a witness that proves that you can get a path. But there's also a witness to prove that you can't get a good path, which is a cut. And so this idea of having witnesses of yeses and witnesses of nos puts it in the class NP intersect co-NP, which is getting further than you want to know. But we'll get to that when we talk about NP. All right? But for now, you can forget all about that, and we're going to try to prove it. We're going to prove for every network, for every choice of augmentation paths, we always find a global maximum. All right? So this idea of roofs on Mars is my idea, so don't expect to see it anywhere else. There's a common idea that is here, is we have a primal problem that we're trying to solve, and then there's this idea of duality, and there's, given any linear program which has a primal problem, you can invert the matrix and find its dual, and so we're going to talk about a primal problem and the dual problem. All right, and so in this case, the primal problem is that a solution is where to stand on Mars, right? There's some topology of Mars, and a solution is where to stand. And of course, there are an exponential number of places to stand. And what is our goal? Our goal is to find the highest place to stand. Right? Everybody got that? It's because we're doing hill climbing. We're looking for a high place to stand. Well, the dual problem is that because the air is so bad on Mars, we've built an exponential number of roofs over Mars, and a solution is one of the roofs. And our goal is to find the lowest roof. All right? So that's the dual problem, right? So the primal problem is to find the highest place to stand, and the dual problem is to find the lowest roof, right? And we do this so that you can see it pictorially, the difference. Really, this is going to be max flow, and this is going to be min cut, all right? But this is a picture, and you know I like pictures. So there are various things that we need to prove, all right? The one thing we need to prove is that every roof is above every place to stand, all right? So you take an arbitrary roof and an arbitrary place to stand, and you have to prove that, well, the roof doesn't go through the land, right? The roof is somehow above. And this roof then gives you, a roof, you can see, somehow gives you then a witness that the solution of the primal can't be any bigger, right? And a solution down here tells me, is a witness that you can achieve a solution to the primal, right? If I'm here, I can say, well, the max place to stand is here or above, right? And if I have this roof, then I know the max place to stand is here or below, right? So we're getting these witnesses that sandwich our solution. Does everybody kind of follow that? And then, so what does that give us? Well, if every roof is above every place to stand, then it follows that the lowest roof is above the highest place to stand, right? You just get that for free, right? So here's our lowest roof, and here's our highest place to stand, and there could be a gap, right, between the highest roof and the lowest place, the highest, right? But what we're going to prove is that there's not a gap, that max flow equals min cut, that the two solutions equal, all right? And how are we going to prove that they're equal? Well, we're going to prove it by using the following algorithm, all right? What we have to prove with our algorithm is that given any place to stand, right? This is a network, is a current flow, right? Given any flow, any place to stand, we want to do one of two things. What's the one thing we might like to do? Go up, get a better flow, right? So that was what our algorithm is doing, is given a current flow, it was finding a better flow. And you find a better flow and a better flow and a better flow. And then when you can't find a better flow, what is it we want to be able to do? It's find a cut of equal value, right? To find a roof that matches. So what we're going to do here is, given any place to stand, our algorithm is either going to find a way to move up and get a better place to stand, or it's going to find a roof that's at the same level, right? So, and can there be a roof that goes through there? No. So when the two are equal, we know that we must have the optimal.
So you just find the local maximum and compare.
Our goal is to prove that there's no local. Here it looks like there's a local maximum, but let's look at that local maximum. Suppose you were standing there in a local maximum, right? Can you move up to a higher place? Not with a single step, right? Because that's the definition of a local maximum, is that you can't take a step up, right? So, but can there be a roof that matches you there? No. So what is this proving us? This proving that this doesn't exist. We're proving that local maximums don't exist. Because what's true about a local maximum, right? You can't go up, right? But it's not maximum. So together that proves that this can't happen. And, right? Yeah, exactly. And, right, everybody kind of follow that? All right, so here, so what is our algorithm? Is to get a better and better and better flow until you get a matching cut. And what we're going to prove now is that we then have an optimal, right? We're going to prove that that the two, now we have, right, the minimum roof, the optimal for the minimum roof is going to equal the height of the maximum place to stand, right? And how do we prove it? Right? Well, again, we prove these two things, right? Every roof is above every place to stand, and the algorithm keeps going until we get these to match. And then, right, then these are all kind of equal. So what's the key here is, right, the minimum roof is definitely below the roof that the algorithm returns, right, less than or equal to, because it's minimum, which equals which by the definition of the algorithm equals the location that the algorithm returns, which is definitely below the maximum location by the definition of maximum, right? So then that gives us this is greater than this, but we also prove that this is greater than this, so everything has to be equal. All right? I'm going a little fast, but we're trying to catch up. Now, these are the two sentences down here that my father would really emphasize. All right? Is this idea of a witnesses. When we're going to run the algorithm until we get a location in a roof, right? A solution to the primal and the dual, a max flow and a min cut that are equal, right? And then the location witnesses the fact that you can obtain a solution this big, right? And it witnesses the fact that the max location isn't smaller than this because I've obtained something that's good, right? And what is the roof witness? It witnesses that the maximum place to stand can't be any higher, right? So this witnesses that somewhere else there's not a better solution, right? Globally, here we know that this is a good solution, and the roof tells us that we can't be higher. All right? Everybody follow that? So the first witness is a location. We're looking for the highest place to stand, right? And suppose you're standing here. What is that witness? That witness is that the highest place to stand is either here or higher, right? And if I'm here, it witnesses that it's here or higher, right? What is this roof witnesses is that it's here or lower, right? And this roof witnesses is that it's here or lower, right? So if you have them matching, then we know that that's the answer, right? Everybody follow that? In fact, let me tell you, we're not doing the test 3, but I'll tell you what's always been on test 3 and maybe gets slipped into the exam, right, is I give you a current flow, and what do? You build the augmentation graph, and you find the path, and you augment the graph, the flow, so now you have a better flow, right? Everybody? And then now we have this flow. You build the augmentation graph, you look for a path, and there is no path, right? So then I ask, what do? Well, you stop. How do you know that you have an optimal solution, right? And no matter how many times I say this, half of you will say, the way I know this is the optimal flow is because there was no path in my augmentation graph, right? The algorithm stopped. But that's not how you know. That's how you know that this algorithm didn't find a better solution, right? How do you prove to your boss that this is the best solution? Is I have this cut, and look at my cut verifies that I can have a better flow than I have, right? So I can very well imagine slipping in the exam the question of, how do you know that a current flow is optimal? And you'll say, well, I have a cut which verifies that.